In this video, we will learn about the definition of partial derivatives. We know that a derivative represents the rate of change of the output of a function relative to its input. So, if we have a function of two variables, like z equals x squared plus xy squared, which we can also write as f of x comma y equals x squared y plus xy squared. The question we want to answer is, what is the rate of change of z with respect to x and y? This is a hard question, and it will take us a while to answer it. To start, let's solve a simpler problem. We're going to go back to Calculus 1 for just a brief moment. The derivative of a function g of x at the value x equals a can be written as a limit. You take the limit of the difference quotient, that is, the limit as, take the limit as h approaches 0 of g of a plus h minus g of a all over h. So that we understand pretty well. So let's go back to our function of two variables. And let's keep one variable fixed. Say, let's take y equal to the constant b. We'll get a function of only one variable. So that function would be just, I'll call it g. G depends only on x. We define that as, take the same formula as f, keep x as a variable, but y is now fixed as the value b. And the formula we would get with our example in this case would be what? Bx squared plus b squared x. And then, all right, let's apply our limit idea. I will take the limit as h goes to 0 of f evaluated at a plus h comma b minus f of a comma b all over h. Now that limit, if it exists, is known as the partial derivative of f with respect to x at the point a comma b. So that is, now the way we write that is we have this stylized d, which we say partial. So partial of f with respect to x at the point a comma b is that limit. The limit as h goes to 0, f of a plus h comma b minus f of a comma b all over h. So that's this partial derivative with respect to x. If we want the partial derivative with respect to y, so again, our partial of f with respect to y evaluated at a comma b is the limit as h goes to 0. In this case, a, the x variable is fixed at a, and so I would have f at a comma b plus h minus f at a comma b all over h. And I could easily extend this to functions of 3 or more variables with the same idea. So we saw that one way we can write this partial derivative with respect to x is using this partial symbol. We could also have just a partial symbol on top with respect to x, meaning take the partial derivative of whatever this is with respect to x. We could also use partial z with respect to x. Nicer notation, or easier to write, is the subscript notation. We'll use that a lot, where we say f and then subscript x to mean the partial derivative of f with respect to x. And then some less common notations we probably won't use is we could use the capital D, meaning a differential form or differential operator, taking the partial derivative with respect to x of the function f, or maybe instead of x, we just put the numeral 1, indicating that we're going to take the partial derivative of f with respect to the first variable. So just like in first semester calculus, we're not going to actually calculate partial derivatives using the limit definition. We will be able to make use of our rules of differentiation, which we will do in a different video.